Hello class, welcome to the Stat 511 Week 10 video on inferences of the population proportion and variance. So in this lecture video, we are going to focus on constructing hypothesis test and confidence intervals for the population proportion P, also taking a look at the hypothesis test and confidence interval for the population variance sigma squared. And then finally, we are going to take a look at some assumptions for inferences. So to begin, let's recall the four-step process of hypothesis testing. To begin, we state the hypothesis, an acceptable alpha level, specify the model, and check the assumptions. Step 2, we calculate the test statistic. Step 3, we define the rejection region and make a statistical decision. Step 4, we state our conclusion in the context of the problem. So let's start by taking a look at hypothesis test for the one population proportion. So some examples of this would be, is the proportion of defective items in a manufacturing process less than a specific value? Or is the proportion of voters who prefer candidate A greater than a specific value? As you can see, we will be using the population parameter P. This is important for us to recognize. In our previous lessons on hypothesis test, we were doing a hypothesis test for one mean or mu. And now we are switching over to examine a proportion. And so we'll be using the letter P, where P is the probability of success in a binomial experiment. I do want to recall that when we mean probability of success, that doesn't necessarily mean that it's the probability that something went correctly. It's really that it's the probability or proportion that is of interest. So in that first example, I said that in the proportion of defective items, well, in this case, the probability of success would be the probability of a defective item because that's the proportion of interest. And so our evidence that we are going to be using for these cases is that our evidence is based on our sample size n and our corresponding number of successes x. So to begin with our step 1, which is our hypothesis, model, and assumptions, the null hypothesis should be written as H0 colon P equals whatever our hypothesized value is going to be. The alternative hypothesis, similar to what we did in our previous hypothesis, is that we have three options based on doing a one-sided or a two-sided test. If it's two-sided, it's P not equal to P naught, or if it's one-sided, it's P greater than P naught or P less than P naught. And again, you shouldn't be writing P naught, you need to be writing the actual value itself. Our model for P hat, which is our sample statistic, it is going to approximately follow the normal distribution with mean being the P naught and standard deviation being the square root of PQ over N, where Q is equal to 1 minus P naught. And as far as assumptions, we need to have a random sample from a large population such that N P naught is greater than or equal to 5 and N times 1 minus P naught is greater than or equal to 5. So essentially what we need to have is we need to have at least 5 successes and 5 failures in order for this assumption to hold. Step 2, we calculate our test statistic, which is z equal to p hat minus p naught all over the square root of p naught times 1 minus p naught all over n. And as you can see by the z-test, we will be comparing this to the normal distribution. And so we may recall from our hypothesis test for mu when our sigma was known, if mu is less than mu naught, which in this case will now become P is less than P naught, then we will reject the null hypothesis if z is less than negative z alpha. And from before, if mu was not equal to mu naught, will now become if p is not equal to p naught, then we will reject the null hypothesis if the absolute value of z is greater than z alpha over 2. And if originally where we had mu is greater than mu naught, we will now have if p is greater than p naught, then we will reject the null hypothesis if z is greater than z alpha. Otherwise, we will fail to reject the null hypothesis. We may also be interested in doing the p-value method, and this also will be completed the exact same way as we did for the hypothesis test for mu when sigma was known. So if our alternative hypothesis is p greater than p naught, then our p-value will be the probability of z being greater than or equal to our test statistic. If p is less than p naught, then our p-value will be the probability of z less than or equal to our test statistic. And then if we have the two-sided test, then our p-value will be 2 times the probability of z being greater than or equal to the absolute value of our test statistic. Otherwise, we will need to fail to reject our null hypothesis. And as is the same for pretty much all of our hypothesis tests, if we reject the null hypothesis, then we will say that at the alpha level of significance, we do not have sufficient evidence to say that the alternative hypothesis is true. And if we do not reject the null hypothesis, then we will state at the alpha level of significance, we do not have sufficient evidence to say that the alternative hypothesis is true. After making this statement, if you need to make a follow-up statement in response to some question, that's all right, but this conclusion does need to be stated. So at this point, I think we're in a position where we can go ahead and do an example. So the DMV in a large city claims that the pass rate for the driving test is 80%. In a random sample of 90 local test takers, 61 passed the test. Do we have the evidence that the pass rate in this city is less than 80%? And we'll let alpha equal 0.05. So first off, if we want to define our parameter, it is P, which is the proportion of all candidates who pass the test. We can now set up our null hypothesis, which would state that P is equal to 0.8, and our alternative hypothesis would be P is less than 0.8, because we wanted to know if we have a pass rate in the city that is less than 80%. And so we can see that we have n equal to 90 drivers, p naught equal to 0.8, and p hat is going to be that sample proportion of 61 over 90, which is equal to approximately 0.6789. Now we can go ahead and check our assumptions. So it was given to us that we do have a random sample. We do need to make sure that it is from a large population, so we need to make sure we have at least 5 successes and 5 failures. So n times p naught, which would be 90 times 0.8, is equal to 72. That's clearly greater than 5. And n times the quantity of 1 minus p naught would be 90 times 0.2, which is 18, which is greater than or equal to 5. A lot of times we don't always have to actually do the multiplication. It can often be pretty obvious. Personally, when I'm doing this in a professional setting, I will usually only examine the smaller of the two probabilities, because I know that if 90 times 0.2, which is equal to 18, if that condition is met, then obviously 90 times 0.80 will also be met. That's just like a little tip of or trick of the trade that you may want to be aware of going forward. So at this point, we do know that the assumptions are met, and so that it is appropriate to use the normal model to perform a one proportion z-test. And so now we can plug into our test statistic. And I apologize, this should say step 2, not example 2. We're not quite at example 2 yet. And so z will equal 0.678 minus 0.8, all divided by the square root of 0.8 times the quantity of 1 minus 0.8, all divided by 90. And so this will give us a z statistic of negative 2.90. And when we're calculating these test statistics, because we are working with the normal table, it is appropriate to round to 2 decimal places. And so at this point, if we'd like to use the p-value method, then since our alternative hypothesis was p is less than 0.8, so therefore we can find the probability of z being less than our test statistic, which is negative 2.90. And so if we use our normal table, we would see that the probability of z being less than negative 2.20 is 0.0139. And so at this point, we can see that since 0.0019 is less than alpha at 0.05, that means we can reject the null hypothesis. So we can say at the 5% significance level, we do not, or excuse me, let me rephrase. We've rejected the null hypothesis, so therefore at the 5% significance level, we do have sufficient evidence to say that the pass rate is less than 80% in this population. And so now at this point, we can take a look at an example 2. A builder claims that heat pumps are installed in 70% of all homes being constructed in Richmond, Virginia. A random survey of new homes in this city showed that 8 out of 15 had heat pumps installed. That's going to be about 53%. Does this provide evidence to conclude that the rate for all homes is different than 70%? And we'll let alpha be 5% level. And so first thing we should do is, of course, an assumption check. And so we have 15 as our n with 70% and its opposite being 30%. So if I do 15 times 0.3, that gives us about 4.5. I'm going to go ahead and round that to be 5. And so we'll say that our pass rate holds. And so therefore it is appropriate to use the the 1 proportion z test. And so filling out, we have the probability for our null hypothesis that p is equal to 0.7 versus the alternative that p is not equal to 0.7. So therefore we can go ahead, plug into our test statistic, and we'll say that z is equal to negative 1.14. If we decide to go ahead and use the p-value method, then that would become 2 times the probability of z greater than the absolute value of negative 1.14, which is equal to 0.1586, which is greater than our alpha values. Therefore, we will not reject the null hypothesis, and we can say that we do not have sufficient evidence to say the heat pump installation rate differs from 70% at the 5% significance level. All right, very good. So let's do one more example, and this time I will work it out a little bit slower, and we can go ahead and use the critical value method because the previous 2 methods I did p-value. So it is often stated that 10% of the population is left-handed. A researcher is suspicious of this claim and thinks the percentage may be greater than 10%. He takes a random sample of 750 people, of whom 98 are left-handed. Let alpha equal 0.05. So to begin with, checking our assumptions, we were given that it was a random sample, and for 10% of the population, if we do 0.10 times 750, that will be clearly larger than 5. And then, of course, 90% of 750 is going to be greater than 5. So our assumptions hold, and it is appropriate to use the one proportion z-test. So now we can begin by writing out the information that we know. So we know that P naught is going to be 0.10. Our X is going to be 98. Our sample size is 750, and we're using an alpha level of 0.05. To state our hypothesis, we have that P is equal to 0.0, and we were asked to see if the percentage may be greater than 10%. So our alternative is going to be that P is greater than 0.10. And now we may calculate our test statistics. This would be 98 over 750 minus our 10%, all over the square root of 0.1 times 0.9 over 750. And this is going to be equivalent to about 2.80. And so we know from our doing the critical region method in the past, we will reject our null hypothesis if z is greater than z alpha, which our alpha is 0.05. So I'm going to pause for a moment, and I'm going to pull up our z table. And so I'm going to be looking for the situation where I can either look up in our table for 0.05 or as close to it as I can get and know that that critical value is positive, or I need to do 1 minus. I always prefer to go and drop the negative because that makes more sense to me. So between 0.0505 and 0.0495, halfway between, we have 1.645. Of course, we can do it the opposite way, which would have been to do the 1 minus 0.05, which would have been 95%, and we would still get 1.645. So now we can go back to our slide, and we have 1.645. So comparing, we have 2.80, which is indeed greater than 1.645. So therefore, it is safe to reject the null hypothesis. And so we can say at the 5% significance level, there is sufficient evidence that the population of left-handed individuals is greater than 10%. All right, very good. So this brings us to the end of hypothesis test for the population proportion P. At this point, I feel comfortable moving on to confidence intervals. So typically as always, we don't generally know the true value of a parameter, in this case, a population proportion. So instead, we do need to estimate it using a confidence interval. And so setting up just like before, we do know that the probability of negative z alpha over 2 is less than z, which is less than z alpha over 2, which is equal to 1 minus alpha. And then remind you, what is 1 minus alpha? Well, on each of the tails, we have alpha over 2, and in the center, where we have our confidence interval, is the area of 1 minus alpha. And so we also know that our z-test statistic is p hat minus p all over the square root of pq over n. So using that information, we can construct a confidence level for p. And so by plugging in, we have that the probability of negative z alpha over 2 is less than p hat minus p all over the square root of pq over n, which is less than z alpha over 2, which is all equivalent to 1 minus alpha. Now, when the n is large, which we know is when we have at least 5 successes and 5 failures, it is appropriate to use p hat and q hat because, well, we don't actually know the true value of p. And so we have then that the probability of negative z alpha over 2 is less than p hat minus p all over the square root of p hat q hat over n, which is less than z alpha over 2, which is then equivalent to 1 minus alpha. So then our 100 times 1 minus alpha percent confidence interval for p is p hat plus or minus z alpha over 2, all multiplied by the square root of p hat q hat over n. And just to reiterate what I said before, what does it mean that to have a large n? Again, minimally 5 successes and 5 failures. And so now at this point, we can take a look at an example. So in a random sample of 500 families living in Pittsburgh, it is found that 340 subscribe to HBO. Find a 95% confidence interval for the actual proportion of families in Pittsburgh that subscribe to HBO. And so we have a sample size of n. We can calculate our p hat is 340 over 500, which is equal to 0.68, meaning our q hat would be 0.32. And since we are constructing a 95% confidence interval, that would imply that our alpha is equal to 0.05. And so we have done this quite a few times, so we do know that then our z alpha over 2 would be z of 0.025, which is equivalent to 1.96. And then therefore we can just plug in to calculate our confidence level, which would be 0.68 plus or minus 1.96 multiplied by the square root of 0.6 times 0.32, all divided by 500, which would give us a confidence interval of 0.6391 to 0.7209. And so we are 95% confident that the actual proportion of families in Pittsburgh that subscribe to HBO is between 63.91% and 72.09%. Apparently a lot of people like HBO. I'm going to go off and assume that this sample was taken when Game of Thrones was at its peak. Okay, so just a quick reminder, if you are doing a two-sided test, then that means you can use the following critical values. Remember, these values are for the two-sided test only. And so it worked in this case, alpha over 2, we had alpha 0.05, so our corresponding critical value was 1.96. All right, so I don't want you to get too attached to that formula we just used because as you can read in your textbook, there is actually an alternative approximation for a confidence interval for your population proportion P. And the reason for this is some very smart statisticians did some work and discovered that that previous formula does not actually have the stated confidence level. And that is a problem because if we are saying that we're 95% confident, we want to actually be 95% confident. So they derived a new statistic, which we will now use as P tilde, and it's equivalent to y plus 2 all over n plus 4, where y is our number of successes and n is our sample size. So what a better confidence interval for our population proportion P would be P tilde plus or minus Z alpha over 2, all multiplied by the square root of P tilde times the quantity of 1 minus P tilde and quantity all over n plus 4. So going forward, I do recommend using this formula over the other one. The reason I introduced you the other one is it is a good way to show you how confidence intervals are derived, and depending on the textbooks you use going forward, the problem with textbooks is they are up to date only as far as they are printed. And so depending on what resources you may use in the future, certain educational material will use the other confidence interval instead of this new method. So I do want you to be aware of both of these ways of calculating a confidence interval for P, and basically be aware of the drawback of the previous formula, although it is probably still used more commonly than it should. And so at this point, let's take a look at an example. During a recent drought, a water utility company in a certain town sampled 152 residential water bills and found that 78 of the residents had reduced their water consumption over the previous year. Let us construct and interpret a 99% confidence interval for the proportion of residents that reduced their water consumption. And so we can now state that we have a sample size of 152. Our number of, we'll say, successes is 78. We were given a 99% confidence level, so that means alpha is going to be 0.01, which, if we recall from our table, that means our Z alpha over 2 is going to be 2.576. We can now go ahead and calculate our P tilde, and so this would be 78 plus 2 over 152 plus 4. And this would be 0.5128. And now if we construct our confidence interval, we have 0.5128 plus or minus 2.576 multiplied by the square root of 0.5128. 1 minus that would be 0.4872 all over 156. Remember, 152 plus 4 would be 156. Using our calculators to simplify, this would become 0.4097 to 0.6159. So we can then say that we are 99% confident that the true water reduction rate of residence is between 0.4097 and 0.6159. You could have made these percents, that's perfectly fine. I would do whatever feels right in accordance to the problem. Generally, I probably would have made these into percents, but I did want to show you that both ways are acceptable. Okay, and so as we have done a couple times is calculating sample size based on our margin of error. And so if we are asked to find a certain sample size given a margin of error and a confidence level, we can use the formula of n times z alpha over 2 squared multiplied by pq all over that margin of error squared. And so we can calculate that how large of a sample size is required if we want to be 95% confident that our estimate of p in example 1 is within 0.02 of the true value. And so we have 95% confidence, and so that's going to imply that our z alpha over 2 value is going to be 1.96 squared. We will multiply this by 0.68 times 0.32 all over that that margin of error of 0.02 squared. And so this is going to give us 2089.8. We will round up to the nearest integer, and so therefore we need a sample of 2090 to ensure a margin of error no larger than 0.02. Excellent. And so just a little bit of a follow-up. So in a more general case, we don't know a good choice for p hat before you take your sample. And so that formula where, the margin of error equals z alpha over 2 multiplied by the standard error of p hat, that's great in the previous example. If you're asked to do this without any prior knowledge, you should use a p hat of 1/2, and then your q hat would also be 1/2. And this is going to be a way to maximize your margin of error, meaning it's going to be the worst you can possibly do. And so in that situation, the formula you should use to calculate sample size is z alpha over 2 squared divided by 4 multiplied by your margin of error squared. And so what this will do is that it results in a margin of error no more than the value of the margin of error you select, no matter what p hat turns out to be. Okay, so that brings us to the end of our proportion section, and now we will move on to our section on the population variance sigma squared. So in general, statistics classes don't focus on the population variance as much as they do the population mean and the population proportion. So I'm not going to do as many examples as I did in the previous sections because it is not something you're going to see as often in your future. And so therefore I felt it was not worth going through a bunch of the examples for each individual alternative hypothesis. So to begin with step 1, our hypothesis, model, and assumptions for the hypothesis test for a population variance. The null hypothesis should be written as H0 colon sigma squared, which is going to be equal to some hypothesized population variance. And then the alternative hypothesis is going to be one of the three options that you are used to, the 2 options for the one-sided test and then for the 2-sided test. Our model is going to follow the chi-squared distribution with n-1 degrees of freedom. And our assumption is that we have a random sample from a normal population. And so our test statistic, I do want you to be aware of, in this class, I used a capital X squared for this statistic. I've gone through and looked at a bunch of different old textbooks when I was preparing this lecture, and different textbooks used a different value. Some used capital X squared, some used T, um, some used S. I saw just a bunch of different ones. The statistic is the same, but um, this part was different. I decided to do capital X squared because it looked similar to chi-squared, and I was trying to keep that visualization going that we have in the previous hypothesis test. So x squared is equal to the quantity of n-1, n quantity multiplied by s squared, which you'll know is the sample variance, all divided by a hypothesized population variance. And so the statistic, again, should be compared to the chi-square distribution with n-1 degrees of freedom. As far as our critical region method, which we may in some ways recall from our hypothesis test from mu when sigma was known, this process, obviously we are not using z-values, but we do have the same sort of concept. So if sigma squared is greater than our hypothesized value, then we will reject the null hypothesis. If our test statistic is greater than chi-squared at the alpha level, if our sigma squared is not equal to our hypothesized value, and this is a little bit different, we will reject the null hypothesis if our test statistic is greater than z alpha over 2, or excuse me, not z alpha over 2, man, I've been saying that too much, our chi-squared at alpha over 2, or if our test statistic is less than our chi-squared statistic at 1 minus alpha over 2. And the reason this is different is if you examine the chi-squared distribution, it is not symmetric. And so we do have to calculate the values at both alpha over 2 and 1 minus alpha over 2 due to the issue of things not being symmetric. And then for the one-sided test, where our population variance is less than our hypothesized value, we will reject the null hypothesis if our test statistic is less than chi-squared at 1 minus alpha. And if the above assumptions, or rather tests, do not hold, then we will fail to reject our null hypothesis. And the alternative way is to calculate the p-value, just like as we had when we were doing the hypothesis test for mu when sigma was unknown. We cannot get an exact p-value. The best we can do is get a range from our chi-squared table. In general, this is not the method I recommend using, but it is a possibility that I want you to be aware of. But in general, I'd rather you use the previous method. And the decision of how we reject and fail to reject using a p-value does still remain constant. As is how we state our conclusions. If you reject the null hypothesis, then at the alpha level of significance, we do have sufficient evidence to say that the alternative hypothesis is true. And if you do not reject the null hypothesis, then at the alpha level of significance, we do not have sufficient evidence to say that the alternative hypothesis is true. And so at this point, we can take a look at an example. But before we do this, I do want to remind you, we are working with variance and consistency. And so the more variable something is, the less consistent it is. So when we're dealing with standard deviations and variance, ideally these values are small. And so in general, that is our goal, for things to be small, not large. So you may want to keep that in mind as you're moving forward if you're trying to determine if something is a good result or not. And that can also be the same where usually in a hypothesis test, we want the alternative hypothesis to be true. That's not always true when we are doing a hypothesis test for the population variance. Sometimes we want our variance to stay consistent. We want it to stay approximately the same. We don't want it changing. Because if our variability changes, then it's harder to predict things. So taking a look at our example 1, the following are interest rates, annual percentage rates for a 30-year fixed mortgage from a sample of lenders in Colorado in May 2013. And we will assume that the population is normally distributed. And so we were given 5 interest rates that range from 3.395 to 3.728. And we want to know, can it be concluded that the interest rates are consistent with a population variance of 0.01? And we're going to use alpha at 0.05. And so to begin, as I always like to do, write out what we know. And so we have a sample size of 5. I went ahead and already calculated that the sample mean was 3.588, and our sample variance was 0.0177. You can go ahead and calculate that on your own, but I didn't want to make this video longer than it needs to be. And that our hypothesized population variance is at 0.01. Also, since we are going to be using the chi-square distribution, it's important to note that our alpha over 2 is going to be 0.025. Our 1 minus alpha over 2 is going to be 0.975. And our degrees of freedom, which is n minus 1, will be 4. We will need that later when we are making our statistical decision. So now we can write out our hypothesis. So our null hypothesis is H naught colon sigma squared equal to 0.01. And our alternative hypothesis is that our population variance is not equal to 0.01. Now we can calculate our test statistic. This would be 5 minus 1 multiplied by our sample variance all over 0.01. And if we type this into our calculators, we're going to get a value about 7.08. Again, the chi-square distribution is not the t-distribution, nor is it the normal distribution. It's not unimodal and symmetric. The values we get are going to be different. So we're not that, 68, 95, 99.7 rule. So if you got values that were greater than 4, it was almost impossible to occur. That's not the case anymore. And so now we can go ahead trying to make our decision. And so we will reject our null hypothesis if our test statistic is less than the critical value of chi-squared at the 1 minus alpha over 2 level, or if our test statistic is greater than our chi-square value at alpha over 2. And so now let's use the chi-square distribution to calculate these values. And so I'm going to pull up my chi-squared table. And so we can remember that we are looking at degrees of freedom equal to 4. And also, let's see if I can do some highlighting. And so now looking for our alpha over 2, that is 0.025, and 1 minus alpha over 2 was 0.975. And so our two critical values are going to be 0.484 and 11.143. So essentially what we will reject our null hypothesis if it's greater than 11.143 or less than 0.484. And so if we go back, so we said we will reject our null hypothesis if our test statistic was less than 0.484 or greater than the 11.143. Neither of these are the case. 7.08 is in between these two values, so therefore we will fail to reject our null hypothesis. And so therefore we can say at the 5% significance level, there is insufficient evidence that the variance is not 0.01. And so we can consider this to be a pretty consistent variance because we were not able to reject our null hypothesis. Okay, so this brings us to our fourth objective, which is to construct a confidence interval for our population variance, sigma squared. And this occurs more in statistics than constructing a hypothesis test for the population variance, just as an FYI. And so if x1, x2, all the way to xn are normally distributed, and we let a be that chi-squared value at 1 minus alpha over 2 with n minus 1, and b is our chi-squared value of alpha over 2 at degrees of freedom n minus 1, then the typo 100 times 1 minus alpha percent confidence interval for our population variance will be n minus 1 and quantity multiplied by our sample variance over b less than or equal to our population variance, which is less than or equal to the quantity of n minus 1 multiplied by our sample variance over a. And we also can construct a confidence interval. Oh, I made this typo twice. We can also construct a confidence interval for the population standard deviation sigma. As we know, the relationship between variance and standard deviation is by taking the square root. So if we take the square root of the previous formula, we can get a confidence interval for the population standard deviation. And so if we take a look at an example, 6 measurements were made of the mineral content in percent of spinach with the following results: 19.1, 20.8, 20.8, 21.4, 20.5, and 19.7. And so we want to say that assuming the population to be normally distributed, we'd like to construct a 95% confidence interval for the population variance, sigma squared. And so we do know that our sample size is 6. I'm going to go ahead and let you know that our mean is 20.3833, and I went ahead and calculated our sample variance to be 0.70167. And so we were given that alpha equals 0.05. So this means our alpha over 2 value is 0.025. And our 1 minus alpha over 2 is going to be 0.975. And therefore our degrees of freedom is going to be 6 minus 1 or 5. And because I know we are going to need those statistics pretty quick, let's go ahead and find them now. So for our chi-squared of 1 minus alpha over 2 and our chi-squared at alpha over 2. So once again, pulling up that same chi-squared values, we're going to drop literally one row down, having our degrees of freedom at 5. Once again, since we have the alpha at 0.05, we need a chi-squared statistic of 0.831, and this time 12.833. So our statistic for the 1 minus alpha over 2 is going to be 0.831. And our chi-squared for alpha over 2 is 12.833. And so now to construct our confidence interval, on top we have our 6 minus 1 multiplied by our sample variance. And we can copy this on both sides. Our chi-squared alpha over 2 was that 12.833, and then the chi-squared of 1 minus alpha over 2 was 0.831. And so by calculating this using our calculators, we have 0.2733 to 4.2218. And so this means that with 95% confidence, the population variance of mineral content is between 0.2733 and 4.2218. Very good. Not bad, right? Really, the hardest thing is just getting the critical values, and even that isn't too bad. So at this point, we are at our last objective, which is to talk about the assumptions. And really, there's only one assumption I want to talk about. So for assumptions, we do know that it's important to have an understanding of the necessary assumptions for statistical inference. And it is equally important to be able to detect violations of these assumptions. There are two major assumptions that we have, and that is that we have the randomness of our sample observations and that the distribution of the variables being studied holds. And so most of these hypothesis test and confidence intervals rely on the population being normally distributed. And so we do need to know how we can check that normality assumption. And so what we can do is we can construct a normal quantile plot, also known as a QQ plot. And as was stated on the previous slide, although I didn't read it, we can't examine an entire population to determine if it's normal. We don't have that ability, but we can still examine the sample and infer whether or not that sample came from a normal population. And one way we do this is with a QQ plot. And so what it does is for a set of data with n values, it finds n quantiles of the normal distribution that are in some sense equally spaced in terms of probability. Then we would sort our data from smallest to largest and pair the data values up with the normal quantiles. We then plot the order pairs and we see if our data match the normal distribution, meaning our points would fall into a straight line. And so the thing about with QQ plots is we can't prove that the data is normally distributed, but what we can say is that there isn't strong evidence against the normal, or rather against non-normality. And because of this, we do try to construct QQ plots at a high significance level. And we do have to be a bit of a leeway with this whole straight line concept, because even if it doesn't fall in the line perfectly, that doesn't automatically mean evidence of non-normality. So let's take a look at some examples, because QQ plots are one of those things that I think it's just easier to look at visually to understand. So here is a simulated example with a normal model. So you can see on the left, we have a nice normal curve, and then it was plotted to a QQ plot on the right. And so you can see that this diagonal line exists, and then we see these open circles, which are ordered pairs. So ideally, what happens is that our ordered pairs follow closely along this diagonal line. Notice that it follows pretty much exactly in the center, but it does go off a little bit on the tails. And that's because when we are constructing hypothesis tests, confidence intervals, looking at a sample, we generally know the most about things that are clustered around the mean. We are less certain about things on the tails. And so that's why on the tails things tend to go off a little bit, because we know more about what's going on in the center. And so to take a look at what a not great looking QQ plot look like would be to look at a simulated example from the log normal distribution. And so taking a look at this, we see that it's clearly skewed, although it is unimodel, but it is skewed. And so if we were to plot the ordered pairs onto a QQ plot, we can see there's strong evidence that this really does not follow that diagonal line at all. And then taking a look at the Cauchy distribution, it is unimodel and symmetric, but if we take a look at those tails, we've got some issues, and we can see here that for a little bit it looks like it follows the normal distribution, but then it really does go way off. And then taking a look at the uniform distribution, which you are familiar with, again, it is those tails that present a problem. It's okay if the tails go off a little bit, but when we have these extreme tails going off the diagonal, then we know we've got a problem. But we do need to be a bit flexible. So this is a QQ plot with some real data. And so if we are looking at the graph distribution, it looks pretty normal to us. Taking a look at the QQ plot, it does pretty much follow that diagonal, but it does go off a little bit at certain points, but it does come back. And so we would say that this is sufficiently normal. Is it perfect? No. But again, when we work with real data, things are rarely going to be as perfect as it is in the textbook setting. And so at this point, now you may be wondering, well, what happens when the non-normality, or rather normality, can't be confirmed in any way, shape, or form? Well, then we have two options. One, we can do a transformation of the data, or we can do non-parametric test. As I've mentioned many times in this course, there is sometimes a difference between what goes on in a textbook setting and a classroom setting and what goes on in the real world. So in classes, we tend to talk more about transformations of the data. You know, we take square roots, we take logarithms, and that's all well and good and is effective and does happen. I know personally in my work, we generally tend to do more with the non-parametric test. You may have heard things about like Monte Carlo method or bootstrapping, and those are all example of non-parametric tests. And what happens with those is that assumption of working with a particular distribution goes off the table and we focus on other aspects. That is a bit beyond this course. Really, what I want you to know is that other methods do exist, but I'm not going to focus on showing you what they are and how to do them. And so that does actually bring us to the end of this lecture. Remember, we've talked about confidence intervals and a hypothesis test for the population proportion and population variance, and a little bit about assessing for normality. You should finish reading chapter 4 this week and complete homework 4. Essentially, for homework 4, in addition to some true and false questions, I gave you pretty much one hypothesis test and confidence interval for means, proportions, and variances. So just so you're aware. If you have questions, as always, please send me an email. Have a great evening.